Dear students, today we will discuss the Newton's rings, the formation of a ring pattern due to the interference of light. The basic theory of Newton's rings is the extension of theory of interference in thin films. Here we are observing the final interference pattern in the form of rings. First time it was observed by the Newtons. That is why the name of this type of pattern is known as Newton's rings. Here we are observing one plano-convex lens which is kept on the plane glass surface. So this is the plano-convex lens and this is plane glass surface. The air trapped between the convex part, that means this part, and upper surface of the plane glass plane, it acts as a thin film. This thin film is not having the uniform thickness, but the thickness is changing. The thickness of the film or air trapped between these two surfaces is 0 at the center where the plano-convex lens is in contact with this plane glass plate, and this thickness is increasing in the outward direction. For our convenience, we have considered the thickness of this thin film of air film at point A is equal to T, small t. Then how the interference will take place in such a non-uniform film? For this purpose, let us consider the one ray incident on this surface at point A. Here ray number 1 we have considered as the incident ray at point A. At A, portion of the intensity get reflect along this direction as a ray number 2. Remaining part of the intensity from A refract into the film of air medium along AB. Further reflection takes place from point B and the ray reflect as a ray number 3. So ray number 2 and 3, they are derived from the single incident ray 1. Therefore both the rays are coherent and they are monochromatic one, having the same wavelength, and they can easily produce the interference pattern. Now here, to find the conditions when these two interfering rays, that means 2 and 3, will give the constructive interference and when it will give the destructive interference. For this purpose, definitely it is necessary to find the geometrical part difference or optical part difference between these two interfering rays and then equate this with the basic condition. Now here from the figure itself, we will try to write the simple geometry, that is geometrical part difference between ray number 2 and 3 is equal to, one can write 2AB. So why we have considered here 2AB? Because AB is the one ray and this ray is also we have considered AB because distance between these 2 points is very small, of the order of 10 to the power minus 8 centimeter. Therefore this distance is equal to this distance we have considered 2AB. This is the part difference between 2 and 3. So this is 2AB. So as AB we have considered as T, therefore we have written here 2T. So therefore optical part difference, just this is the multiplication of refractive index into the geometrical part difference. This is equal to 2 mu T. Mu we have considered refractive index of the air or thin film trapped between plano-convex lens and the glass surface. So optical part difference equal to 2 mu T. Further, to write the true optical part difference, it is necessary to check the reflections of ray number 2 and 3. So here we are observing the ray number 1 get reflected from the surface of air medium, that is rarer medium. No phase change takes place there. But the AB get reflect from point B from the surface of denser medium, and there is the phase change of pi radians or 180 degrees, which is equivalent to path change of lambda by 2. So we have written here true optical path difference equal to 2 mu t plus lambda by 2. If this path is equal to integral multiple of wavelength lambda, then constructive interference will take place. That is, if 2 mu t plus lambda by 2, this is the path difference, is equal to integral, m is the integral, any integral multiple of lambda, then constructive interference will take place. In this case, bright ring will be observed. Or if delta is equal to odd integral multiple of half wavelength lambda, then destructive interference will take place. That is 2 mu t plus lambda by 2 equal to 2m plus 1 odd integral half wavelength lambda by 2. This is dark ring. So equation number 3 and 4 will give the conditions for constructive and destructive interference respectively. Further, in this case, if we write the small t, because t is changing everywhere, it is very difficult to find the perfect value of t at the given location. Therefore, if we write this t in terms of some measurable parameters, so measurable parameters may be the radius of curvature of plano-convex lens. We have considered here r, and the radius of the rings observed. So here, this distance, if I extend this convex part of this lens, it will form a one sphere. This is the sphere, and if now this is the center of the sphere, definitely this will represent the radius of curvature of this lens. This is capital R, and now here this small r is the radius of dark or bright ring. So at point T, there can be the any ring, maybe first, second, third, fourth, fifth, sixth, seventh, etc. nth ring. So we'll consider here nth dark or bright rings. So by replacing this T in terms of capital R and small r, one can rewrite the above conditions like, and simplifying this one. So dm square equal to 4r n lambda divided by mu. This will be the condition for bright ring, and dm square equal to 2r 2n plus 1 lambda by mu. This is the dark ring, so where dm is the diameter of mth dark or bright ring. Here mth bright ring and here mth dark ring. Further, if I consider diameter of m plus pth dark ring or bright ring and diameter of mth dark ring, and if I reuse these two equations, and after simplification one can write this one simply, d square m plus p minus d square m equal to 4r p lambda. So using this basic equation, you can find the different or various parameters which are unknown in this experiment. For example, if you would like to calculate the wavelength of the light used, so you can rewrite this equation, lambda equal to d square m plus p minus dm square divided by 4rp. So in this case, capital R is the radius of curvature of plano-convex lens. This should be known to us, and p is the ring number. So here, measuring the value of diameters of m plus pth and mth dark ring, you can find the wavelength of light source. Not only this one, by knowing the wavelength, you can find the radius of curvature of plano-convex lens also. So in short, these are the mathematical equations of Newton's ring theory. Here we are observing here the Newton's ring pattern at the center for reflected light, especially we are observing the dark spot, and here different dark and bright rings. As the ring number increases, definitely the spacing between them decreases. Thank you.